All right, since I just learned how to read one of these, I'm going to help you guys read how to learn one of these. You know what I meant. So this right here is a pressure-specific volume diagram. And what that means is, so we have, density is kilograms per meters cubed, right? That's how much mass is in each set volume. Well, the specific volume is the inverse of density. And so what that is how much volume a specific mass will take up. In this case, how much volume in meters cubed will 1 kilogram of whatever substance you want will take up. I think in this case it could potentially be water. And so what this is here we have the liquid phase. Everything past this is the liquid phase. Where pressure is, as you can see, you can increase it and the specific volume will actually decrease because it's getting denser. And you'll notice this line right here, this is the vapor, I think it's called the vapor dome. And what that is the dividing line between where it starts to boil at whatever temperature. So this isotherm right here, as the pressure is decreasing, the volume or the specific volume is increasing because the density is decreasing, and it's starting to expand, and then it hits this dome, and then it goes into this equilibrium where the specific volume is increasing without the pressure changing because it's in between liquid and vapor phase, so there's not going to be much of a pressure difference. And then you have the vapor phase afterwards, and this is below the critical temperature, where it's going to be like a vapor that could potentially condense. So everything here is a liquid that could potentially boil. And you'll notice once you go above the critical temperature, you're in the gas region, where if you have an isotherm, it'll just be like this shape. It's not abdiatic, or however you pronounce that. This is where you're going to you keep the temperature the same, and this is how the pressure will increase with the gas, and they'll look increasingly more like this as you get above there, and it'll just look like that. And then everything here will start to almost just look like a straight line as this goes to a solid, because once you have a solid, pressure does not matter. So, but why I have these in orange is because these are phase, like these separate the phases. So this critical temperature isotherm right here, as the pressure goes down, the specific volume increases because the density is decreasing because it is expanding. So what that means is that as you reach this point, the vapor and the gas start to have the same properties. Like they get very much more similar as they converge. So once they converge and they have the same properties, you're at the critical point, and you then have a fluid. So, and the properties of a fluid are going to be in between that of a gas and a liquid, because that's what it is. It's a gas and a liquid at such an equilibrium that it's indistinguishable from each other. And up here, I have written the van der Waals equation of state, which is, you'll notice it's very similar to the ideal gas law, except it's got some more variables in there. So what these variables are, this B right here, van der Waals decided that molecules take up space. So this B is the space that those molecules take up, the excluded volume. And this A is the attractiveness, like the attraction force between those molecules, because not every gas is going to be perfect. So this accounts for that. And so you have your temperature over volume minus your attractive force. And this is specific volume, which you can have an M right here to let you know that it's a specific volume, and an M right here also to let you know that that's the specific volume. That's not just any volume. And you'll realize that you can derive these. I think my marker's running out. Yeah, my marker's definitely running out. You can derive these A and B by realizing that right here it starts to get very, very flat, and as it gets flat, the derivative approaches zero. The derivative with respect. Yeah, I need a new marker. the derivative of the pressure with respect of the volume at T is equal to the critical temperature is equal to negative RT, and this is RTC, over V minus B squared plus 2A over V cubed. And you'll realize that this derivative here, you can barely see that, but you realize this derivative here is equal to 0 because this line is flat. And that's the definition of a derivative, or no. And also, if this is flat, and you'll notice as it also goes, it goes from concave up to concave down, which makes it an inflection point as well. So when you take the derivative of this, or the partial derivative of pressure with respect to the specific volume at the critical temperature, which is, let's see if I do my math right, 2R critical temperature over volume minus the excluded volume cubed minus 6A over V to the fourth is also equal to 0. And I'm now going to show you how to derive A and B from this. Just checking my notes over here. And so we can solve for A first by multiplying the first and second derivatives because they're both equal to 0. So if you multiply them together, they're still going to equal 0. And that makes this significantly easier to eliminate A. So negative, so RTC over V minus B, which is the specific volume minus the excluded volume, squared, is equal to 2A over V cubed, which, since it's equal to 0, is also equal to this second derivative, 2 times R times the critical temperature over specific volume minus excluded volume cubed is equal to also 6A over V specific volume to the fourth. Yeah. So what you're going to do is actually cross multiply. So it's things cancel out. So V minus B cubed over 2RTC is equal to V to the fourth over 2A, and this is all bleeding together. No, sorry, it's not 2A. No, this is 2A. This is 6A. And then we have, so these cancel out. This cancels out. A cancels out. V, the cube cancels out. This becomes 3, so it's volume, critical volume minus excluded volume over R times the critical temperature is equal to V over 3. And from there you can solve for B, which I'm going to do, is V critical, this is all VCs, I'm being lazy at the moment. Just assume this is all VC, so V is equal to, V RT over 3 minus VC is equal to B. Wait, I'm an idiot. Okay, no, it's not the 2 that cancels out, it's the RTC that cancels out. So it's actually VCB over 2, which means not VRT. Cross multiply, so 3 volume minus 3B is equal to 2 volume. So then negative 3 volume is equal to, no, negative 3B is equal to negative volume. So B is equal to volume over 3. So B is equal to the critical volume over 3. That is how I derived B. And then from there, I can derive A just by plugging this back into the derivative, which is negative R critical temperature over V minus volume, critical volume, minus, so we found that P is equal to critical volume over 3, so it's V minus V over 3 squared is equal to 2A over V cubed. And no, it's not negative. It's because it's set equal to each other. So then you have RTC is equal to, oh no, RCT over 2/3 V, because it's 1 minus 1/3 squared, is equal to 2A over V cubed. And so you got RT, I'm doing this all sorts of out of order, but you're watching me write it, so RT over 4/9 V squared is equal to 2A over V cubed. And then you're going to flip this so it's 9/4 RT V 9/4 RTV is equal to 2A. So therefore A is equal to 9/8 R times the critical temperature times the critical volume. That is A. So from there, if you can even read this, we have derived A and B from the van der Waals equation using this as our guidance. Hi, it's me from about an hour and a half in the future. I realized that I forgot something very important for this video, the compressibility factor, Z. Okay, and I got this. Okay, I got this marker to work like 2 seconds ago. There we go. Z. So what Z is the compressibility factor of a gas or a fluid. And normally, and it's PV over RT. So normally, like an ideal gas would be a compressibility factor of 1, right? No, we don't deal with ideal gases in this class. So we need to derive this right here. But how are we going to do that? Well, to start, I'm going to do something very unorthodox and give myself some room with which to write. Hi, it's me again. So you'll notice I'm wearing different clothes from the last time I did this. The reason why, I made a serious mistake, and going through the editing, I just decided I would redo this part entirely. So where I left off, where before I made the mistake, was I erased everything, and now I've just rewritten the critical compressibility factor is equal to the critical pressure times critical specific volume over R times the critical temperature. And from here, I'm going to be deriving what the critical compressibility is equal to, as theorized by van der Waals. So, where I left off, PC is equal to RT over V minus B minus A over V C squared, right? And then since we have already derived A and B, we have that as equal to RTC over VC minus 1/3 V, or just VC over 3, to make it simple, minus, I believe A is 9/8 RT VC over VC squared. The VC's cancel out. This becomes PC is equal to RTC. Well, it's just 3/2 because this will become 2/3 VC, so 3/2 RTC over V minus 9/8 RTC over VC. And then doing the algebra there, PC is equal to 3/8. That is a terrible 3. 3/8 RTC over V. And since critical compressibility is equal to PCVC over RTC, then PC over RTC is equal to 3/8 RTC over V. So this is multiplied over. Actually, no, you divide it over. So that's why this is equal to Z. Z is equal to 3/8. Or the compressibility factor at the critical temperature is equal to 3/8. And it's just a constant. And so you'll notice that's very far from the Z is equal to 1 that is supposedly at ideal gases. So at critical temperature, or the critical point rather, Z is, or the compressibility factor is not equal to 1. So it's not ideal.